Okay.
Both remote.
Okay. Is it working now?
Yeah.
Okay. Can I start?
Yeah, please.
Okay. Good morning. Good afternoon, everyone. My talk today is the overview of the hadron spectroscopy at Belle and Belle II. My name is Junhao, and I will talk on behalf of Belle and Belle II collaboration. The theory and the experiments inspire each other, and for years this circulation works well. However, since this century, a lot of unpredicted phasors or particles are discovered by LCB, Bell, Baba, Bessie, and Cleo, and a lot of those particles and phasors could not be described well with conventional serial pictures. All these stories start from the discovery of X-3072, which was first observed in the environment mass of a pi J the unexpected mass and unique properties quickly grabbed everyone's eyes since once the X-3072 is discovered. Ever since then, there are the Y, not only X particles, the Y particles, even the pentaquark or the double charm Baryon states are observed. Until now, this observation of X-3072 has been the most cited Bell paper. To explain those states that we observed, there are a lot of models For example, the compact tensor quark, the hadron Quarkonium, or the hadronic molecular, or even hybrid or global. The hadron spectroscopy provides new knowledge that feeds back to the theory, and it's also a perfect ground to test the theoretical models. The hadron spectroscopy also provides new viewing angles toward the QCD series. In this picture, you can see that we show the mass scale of the spectroscopy for the hadrons. For the lower mass, we could study the baryons, and the energy goes on. We have a charmonium and a bottomonium. Firstly, let's have a quick view of the Belle experiment. The KKB is the asymmetry E plus E minus collider operating near the open force mass peak. The world record of the luminosity is 2.1 times 10 to 34. The total integrated luminosity is almost 1 inverse 8 bar. The benefits of the hadron spectroscopy at the B factory is that the B factory has the efficient reconstruction of the neutrals, and we can also have a fully reconstruction of the recoil system. There are varieties of a production mechanism to produce the different hadrons, and the large production rate of B2CC bar also provide a solid ground to study the charmonium particles. The unique data set on the Beats factory also provide a unique view to study the hadron spectroscopy and the QCD series. Here is the Belle and Belle II capabilities on the spectroscopy. For the low energy particles, we can work on the UDS baryons, charm baryons. Then we, as the energy goes down, we can have a charmonium or the CC baryons, CC bright pentaquarks, or the double charmonium particles, and the Bottomonium particles. We have 5 different production mechanisms for the Quarkonium states, including BDKs, initial state radiation, double charmonium production, 2-photon process, and the prompt Bottomonium production in the E+ E- annihilation. This is the Quarkonium spectroscopy that we have. We have a good agreement with the potential model below the open flavor threshold. But for the particles above the open flavor threshold, the exotic state, which is also called XYZ states, they are not, they do not agree with the potential model, or even worse, some of those are not even predicted. Let's focus on some results that we have that Belle have already achieved. First is the BDKs. The large production rate provide a solid ground to search for the exotic states. In the history, the observation of X372 is, of course, a great success, and we do not, and not only this, the established of various the DC states is also bring a lot of interesting particles. For example, in the K-pi psi prime, the signal of DC 4430 was observed. And not only this, in the DC 4050, DC 4250 were also observed in B2 K-pi Kc. The significance are all greater than 5, and amplitude analysis is performed to the B2 K-pi J-psi, and the signal of DC 4200 and 4430 are also found. In the initial state for the initial state radiation, this process allows us to reach lower center of mass energy for free. Belle also achieved a great success in the history, which is the observation of DC 3900. This is the first solid 4 quark states that we have observed. This is the firstly thing in the E+ E- goes to pi J-psi, and on the one pion with the J-psi environment mass. And evidence of this of 4020 was also found on pi psi 2s environment mass. Recently, a new vector state in the E+ E- go to DS1, DS2 star is observed. So on the environment mass of DS1, you can see a clear signal with the significance of 5.9 sigma is found, and on the environment mass of D sub S, DS2 star, 3.4 sigma evidence is found. The mass of this new vector state is measured around 40 4620 MeV. It's quite close to the so-called Y4650. But if you look at the error of this, if you look at the error of this state, it's quite far from like 3 sigma far from the so-called Y4660. We still need a lot of studies to separate whether this is same state or not. The double charmonium production is a unique field to produce the charmonium or charmonium-like particles. KC03860 was observed in the E+ E- goes to JSI D bar. And the X3940 was observed in the JSI recoil mass, which is dominantly decays to DD star. According to this study, the cross-section of the double charmonium production contains the JSI is measured to be 0.774 inverse picobar, which means there will be a rich resonance will be produced against JSI if we have more data collected on Belle2. The two photon process also provide a unique field to produce the charmonium-like particles. In this process, a lot of exotic states are established in various final states. Firstly is the X3930 to DD bar. You could compare with you can compare this particle with the previous X3860 and 3940. You can see that they are this is not the mass of this X3930 is not consistent with the 3860, but the more consistent with the 3940, which is dominantly decays to DD star. This is remains a puzzle to us. On the invariant mass of omega JSI, the X3915 was observed with the 7.7 sigma. On the invariant mass of phi JSI, there is no signal of Y4140, but evidence of 4350 was found. Recently, in the two photon process, the X3072 signal decays to Papa JSI was found as evidence with the 3.2 sigma. This tells us that in the two photon process, one or both of the two of the photons could be virtual and may provide a new mechanism to the X3072 production. And recently, on the two photon process to the gamma psi prime, evidence of 3920 is found here, and a new hint around 4.02 GeV is found. For the Bottomonium production, this provide an excellent playground for the NRQCD, and it also contains unique properties. Firstly, a question will be raised: is the so-called epsilon 5s is what we believed? The PDJ number for the Upsilon 5s is the Upsilon 5s mass is colored the pink bar on this diagrams. However, if you look at this left plot carefully, you can see that the peak value is not converged to the measured cross-section of the red dots, which is the measured cross-section of E plus E minus goes to B star bar, while the black dots are the total BB bar cross-sections. However, if you look at the other cross-section measurements, for example, the middle plot, which is the pi HB 1p and pi HB 2p, the peak is on the peak of the cross-section is on the right of the so-called 5s mass. This is a similar peak is found on the pi upsilon 1 to 3s cross sections. This gives us a question that why these peaks are differently, but they are all close to the upsilon 5s mass. If we look at the left figure again, we can also see that there is an axis between the measured BB bar cross sections and the B meson pair cross sections. The axis come from the BB bar, the B meson pair with multiple pairs and the Bottomonium transitions. And this gives us a question that, this gives a very high abnormal transition rate for the Bottomonium. From this figure, we can see that the transition rate for the upsilon 5s to pi upsilon 1s is about 100 larger than the Bottomonium below the open flavor threshold. This also leads the observation of ZB 10.6, 10 and 10.6, 15. This ZB state was also found in the pi HB transitions, which provide an essential contribution to this pi HB transition rate because there is a spin flipped in this upsilon to HB transitions. Well, it should be, the transition rate should be very small. However, as you can see, that this transition rate is compatible with the pi upsilon. I would say that this similar feature is also found in the higher charmonium states, which also gives us a good view to better understand the correlation between the charmonium and the Bottomonium states. Then let's move to the Baryon spectroscopy. The baryons could be produced from the fragmentations and the B decays. In this talk, we will focus on the searching for the new states on Belle and the property measurements. Recently, we have fruitful results, but we will only focus on the few topics that we are listed here. Firstly, the searching for the new state. The various production mechanism will create massive baryons. The lower background by the E plus mass settings will also give us a good benefit to searching for these new states. Firstly, the evidence of the omega C to pi omega 2012. This omega 2012 was observed by Belle, and according to the theoretical calculation, if this is the cake C molecular, it would be much more visible in the omega C0 to pi cake C. And an evidence is found in the 2 in the 2D simultaneous fit to the kick C invariant mass and the pi omega 2012 invariant mass. On the radiative decay could also be searched on the Belle because of the good reconstruction efficiency of the photons. Evidence of a lower state are to 2700 was found on the invariant mass of gamma KC, and a much much more enhanced peak was observed near this small peak. On Belle, we can also do some property measurements. For example, the spin parity determinations. The spin could be determined by the helicity angle, and the parity could be determined by the transition rate. On the left two figures are the helicity angles of theta h and theta c, which is defined here. The most consistent, the fit result is mostly consistent with the spin 1/2 hypothesis, and this also exclude KCC to 2645 spin over 1/2. The ratio could be used to determine the parity because this ratio is sensitive. According to the theoretical calculation, this ratio would be very close to 1.06, and compared with the experimental calculation, this positive parity is assigned to this particle. Then let's move to the Super KB and Belle II. Super KB and Belle II is a next generation B factory. We have upgraded detectors and an accelerator. With the benefit of a nano beam, we can have almost 30 times larger integrated, 30 times larger instantaneous luminosity and almost 40 times of integrated luminosities. For the Belle II, the tracker system is upgraded, and so as the QM and the software part. By now, we have already achieved 250 inverse Fugger, and the luminosity is increasing by 1 or 1.1 to 1.5 inverse Fugger per day. The maximum luminosity record is 3.8 times 10 to 34. The target of at the summer of this year, we will have a launch shutdown to upgrade the detector. We target to have 500 inverse Fugger data at that time, and the baseline is 480 inverse Fugger. Here is our prospect. In short term, accumulate around 5 inverse Fugger upsilon S before the launch shutdown before the summer this year may not bring a significant change into the arena, but if we combine Belle and Belle II data, we may at least clarify some puzzles. For example, there is an extra resonance beside X3872 on the invariant mass of omega psi. This is firstly clarified. This is firstly claimed by Belle and Belle. And recently, the Belle III published the environment math, the study of omega J psi, but it's very difficult to tell whether this is whether they are one particles or two. So if we have an extra 500 data, we could at least say something on this. Another prospect is a new white state is observed in the pi pi epsilon environment mass around 10.775 GeV. However, limited by the luminosity, there is only like one inverse Fickle at each scan point on Belle. Based on that, if we have we have later data, we can tell a big story on this new state. In November last year, we have an energy scan around at the peak of 10.75 GeV and also 3 points around this energy. In total, we have like 20 inverse Fickle data. The physics goal would be understand the nature of this Y10750, and there are several potential analyses. For example, E plus E minus go to pi pi epsilon and omega kb, B meson pair, B star meson pairs, or gamma XB studies, and the result will come in soon. If we can accumulate 10 inverse Fickle data, we can clarify some evidence that raised by Belle and other experiments. For example, on the environment of fragile side, we can have a better understanding of this particle to confirm or reject this particle, and also some other Z particles in the key pi J psi or key phi J psi analysis. We can also perform an amplitude analysis to the J psi recoil mass to determine the spin parity of this X3940 particles. If we have like 50 inverse Fickle data, we can fully cover the charmonium region with ISR process. A dedicated analysis to the E plus E minus 2 pi pi J psi, KK J psi, or other charm-Baryon pairs production regions. The ZC production in both E plus E minus annihilation and B decays will also give us a good understanding to these natures. The double charmonium states production could be also covered in the ISR region. For instance, the E plus E minus go to eta CJSI or KCJSI. For other prospects at Belle II, we could have very high statistics samples of epsilon 4s. A dedicated study of X3072 decays to the final state with the neutrals would be very interesting. For example, the D0 D0 star. You can check more details in Soren's talk after a few days. We can also searching for some new charmonium-like states in various productions or the amplitude analysis. The higher statistic samples over the epsilon 5s and 6s will allow us to investigate the ZB states, including the quantum numbers, the neutral panels, the decay modes, We can also search for the new Bottomonium-like states, and we can also this large Wupson 5 and 6s states can also provide a potential laboratory for other Bottomonium states like HB or Wupson D states. And the Belle2 is also potential to reach higher center of mass energy. For example, the lambda B bar pair region. In a summary, even a decade after data taking finish, the Belle experiment is still producing interesting and important result. Belle2, the next generation B factory, can make significant impact in the spectroscopy, including but not limited to the precise line shape measurements, quantum number determination, search for new decay channels or new states, and so on. The efforts will goes on with upgraded facilities, over KKB, collider, and Belle2 detector. Okay, that's all. Thank you.
Thank you, Junhao, for this very nice overview. We are open for questions and comments. Julian. Yeah, please.
Yes, it's me. Okay, yeah. Let me see. I wanted to make a comment. I mean, again, in page 13, you have the talk again a bit about this GC0 3860 that I made a comment before when the LHCb talk was given. I think, I mean, LHCb, yeah, LHCb has ruled out that state, yeah. Page 13, page 13, 13, 1, 3. 1, 3.
Sorry, I have something wrong with my computer. Please wait a second.
Well, anyway, I mean, I will say it's okay. The X0 HC0 3860, that you, this one, that's it. XC0, GC0 3000 was observed in E plus minus? No, no. I think, I mean, after the observation, I mean, and the very good analysis with good data of LHCb, you should not claim that anymore. I think you should remove the claims for that. Apart from the work that apart from the work that of ours that I have mentioned before, there is an excellent work right now from Mark van der Heaven, analyzing gamma going to DD bar. Well, it was also claimed that state, and they see again that there is no signal at all of that state. So I think please, I mean, I would advise, I mean, you just to remove the claims. There is no reason for that anymore. Okay, now, I mean, in the page 18, you have something there if, concerning the Omega 2012, which I think you have made a mistake in the writing. I mean, I tell you, I mean, but I think there is a mistake in the writing because 18, page 18, 1.8. Yeah, you see that if is a molecule could be much more visible in omega C pi plus, no, because 1 pi plus comes from the decay, and then you have the Omega 2012 decay, which can decay into K bar cascade or K bar cascade bar, and then there is a K bar cascade pi. So there are 2 pions. So this is not well written. And in any case, you know, I want to mention, I mean, there are 2 independent works. One is by Xie Jujun and colleagues of yours, Xie Jujun and Lisheng Geng, and independently is one from Toledo and Ikeno, in which they show, I mean, that there is no problem. The data of Belle, I mean, can be explained within the framework of the molecule. 2 independent works, they agree on the conclusions. And finally, to finish, I mean, one recommendation, you know, I would recommend, I mean, the Belle collaboration, particularly all experimentalists, but particularly the Belle collaboration, to provide data which are efficiency corrected. You said in the introduction how important it is that there is, I mean, work, I mean, between theory and experiment. If you don't give us the data which is efficiency corrected, we cannot compare. So, and you know, my experience is that all the data that I had, I mean, to I mean, reproduce from Belle, all of them, were not efficiently corrected. Some people have been nice, to in private give me the corrected data, and others laugh at me even, they had, the shame of laughing at me, saying that I could not reproduce the data because they were not efficiently corrected. That is something insulting because, the first thing, of an experiment is that it should be reproducible. And if you don't give us the data, which are efficiently corrected, we cannot reproduce it. Okay, so please take that into consideration and make a favor to us theoreticians and to the community to give the data.
This is a general comment to all the experimentalists, not for this talk only.
This is correct, but at least I have had the same experience with the LHCb. But the LHCb, at least they were giving me the data with a phase space. Phase space, correct, with the efficiency, that they had. And then from there, I could reproduce, the data efficiently corrected. But that I didn't have a chance, with the Belle data ever.
Okay, so thank you for the comments. I think, is there any other questions, comments to this talk? Hi, Junhao. In fact, I have one question. You mentioned spectroscopy can, in principle, run at high energy. So how high can spectroscopy reach?
Yes, so currently we don't have some numbers on this estimation, but this is just a proposal. Yes, just a proposal to the accelerator side that we want to have a higher energy to the, for example, lambda B bar energy regions.
Okay, I think in your slide 21, you mentioned the short-term plan to accumulate 500 units Belle data by next year.
This is the.
No, this is the plan. I just wonder how is this 500 units Belle data compared to around 1,000 units Belle data at the Belle 1. I think the efficiency could be a bit different and the resolution could be better. So how to expect the final result?
Well,
for example, for B to X3072 plus a K-on. So we expect a significant improvement.
We do have a better resolution for the check for the momentum, and of course the increased luminosity is the most important thing that I in my thought. So on the study of X3072, I think we can improve. We don't have too much, I would say. We can improve the analysis of omega JSI, and yeah, I think that's what we can do with the 500 more data that we have.
Thank you. So are there any other questions or comments? Yeah, it seems not. So thank you, Junhao, for your talk.